it's almost the time. Okay, so let's begin. Welcome to the afternoon session, particle physics session. We have 4 speakers. First speaker is Tobias. He will talk on the singly charged scalar singlet as the origin of neutrino masses. Please.
Yeah, thank you very much. As already mentioned, my talk is on the singly charged scalar singlet as the origin of neutrino masses. So welcome everyone. And before I start, I would like to express my gratitude for this nice opportunity to contribute a talk to PASCOS. And I would also like to acknowledge my collaborators, Michael Schmidt and Juan Herrero Garcia. Okay, so let me give a brief motivation for our work. So we all know that there is conclusive evidence that neutrino masses are non-zero. And of course, there are myriads of models on the market which explain these neutrino masses and which also give predictions for the implications at low energy. But our approach was slightly more, say, systematic in the sense that we wanted to look at a whole class of models, namely those which feature a scalar particle, which I call H, that is a singlet under the strong interactions and the weak interactions, and which carries 1 unit of electric charge. And there are at least 2 reasons why it is interesting to study this particle. The first is that it indeed features in several well-known models of radiative neutrino mass generation. And on the phenomenology side, there currently are intriguing hints for the deviation of Flavian universality in the lepton sector, which the singly charged scalar singlet could explain. And so in the following, I would like to explain how we studied the generation of Majorana neutrino masses in our kind of minimal science model extension, including the implied phenomenology at low energy in a model-independent way. Okay, so here you can see the Lagrangian of the theory. We have the standard model Lagrangian, we have the standard kinetic term, the mass term for H, and we have this coupling of H to 2 left-handed lepton doublets, which is the only renormalizable coupling of H to standard model fermions. And quite importantly, the conservation of lepton number is respected by all the renormalizable terms in this theory, and therefore one can assign units of lepton number to the leptons and to H as indicated here. And due to the way the 2 left-handed lepton doublets in this coupling are contracted in weak isospin space, the associated matrix always has to be antisymmetric in flavor space. And therefore it features a non-trivial eigenvector that you can see here with a vanishing eigenvalue. So for our analysis, the only assumption was that when the main contribution to neutrino masses is generated, we require that either one of the neutrinos on the external lines couples to the rest of the associated Feynman diagram via the coupling YH, while the other neutrino couples differently, or we require that both of the external neutrinos couple via YH. And we call these 2 cases the linear case and the quadratic case. And I hope it will become clear soon why we chose these designations. In the linear case, the generation of neutrino masses proceeds schematically as can be seen here. Excuse me. And so the black dot signifies the coupling YH, and the dashed line indicates the propagator of H. And all the rest of the relevant interactions which enter the generation of neutrino masses here are indicated by this gray blob. And I want to be as agnostic as possible about what's going on here. I only have to assume that there is a source of lepton number violation, because otherwise I do not obtain Majorana masses for neutrinos, and there have to be at least 2 insertions of the standard model Higgs web in order to generate the Weinberg operator. And then the resulting neutrino mass matrix is just given by X times YH, where X is a matrix which contains all the information about what's going on in the gray blob. And since in the Miranda case, the neutrino mass matrix has to be symmetric, I also have to add the transposed version of this contribution. So one immediate phenomenological consequence of the linear case is that since we do not specify the matrix X further, the determinant of the resulting neutrino mass matrix is in general not zero, and therefore all three neutrinos will receive masses. And now I can take this equation for the neutrino mass matrix and multiply it by the eigenvector VH from the left-hand side and the right-hand side, and then obtain zero on the right-hand side of the resulting equation, because on the right-hand side, we always hit one of the matrices YH, and the eigenvalue was zero. Okay, so the linear case can be realized in a model-independent way via this effective operator at dimension 5, which is suppressed by a large scale lambda and which would violate lepton number by 2 units. And then the resulting neutrino mass matrix would be approximately given, as can be seen here, up to a loop function, which is not explicitly stated. So neutrino masses would be generated at one loop level, which is why we have the factor 4 pi squared in the denominator. And since one of the insertions of the standard model Higgs web would be associated to a chirality flip on an internal line, neutrino masses would also be proportional to the masses of the charged leptons in the standard model, which are contained in matrices in the matrix YE. But in principle, now this structure can be compared to what is known about the neutrino mass matrix from experimental data. The linear case is also realized in terms of concrete models. A very important example given by the so-called Z model, in which the particle content of the standard model is extended by H and a second Higgs doublet. And then the coupling of H to the two Higgs doublets in the theory violates lepton number. Another slightly more involved example can be seen on the right-hand side here, where neutrino masses are generated at 3 loop level, and the particles running in the loops are assigned to larger representations of SU2 weak isospin. But in order for the classification in terms of the linear case to apply, the details of the loop structure are actually not relevant. Okay, in the quadratic case, both of the neutrinos on the external lines couple via YH, and now this unspecified lepton number breaking physics, signified by the gray blob, gives rise to a matrix that has to be symmetric and that we call S. And here the neutrino mass matrix is quadratic in YH, this is why we call it the quadratic case. And since YH is antisymmetric, the determinant of this neutrino mass matrix will vanish by construction. And therefore, at this leading order, one neutrino will remain massless, which of course has some implications for experiments which probe the sum of the 3 active neutrino masses. And here it is sufficient to multiply this equation of the neutrino mass matrix by the eigenvector VH just from one side in order to obtain 0 on the right-hand side. The quadratic case can also be realized in terms of an effective operator, then in a model-independent way. And the resulting neutrino mass matrix would be quadratic in the charged lepton masses, because here both of the standard model Higgs web insertions would be associated to chirality flips on an internal line. In terms of concrete models, an important realization of the quadratic case is given by the Z-Babu model, in which the particle content of the standard model is enlarged by H and a doubly charged scalar singlet K, the coupling of which to H violates lepton number. And if one integrates out K, one would in fact get back this effective operator just introduced. Another important example is the Krauss-Nernst-Trotten model, or KNT model, in which there are 2 copies of H, one of which is charged under a Z2 symmetry. And there also is a neutral fermionic singlet, which is charged under Z2 in order to prevent the standard seesaw mechanism from kicking in. But as in the linear case, in order for the classification in terms of the quadratic case to apply, the details of the loop structure are not relevant. Okay, so we derive these expressions in the light blue box which directly relate the couplings of H contained in this eigenvector to measure data on the neutrino mass hierarchy and mixing contained in matrices M diagonal, which contains the active neutrino masses, and the PM&S matrix U. And we interpret these equations as conditions which necessarily have to be satisfied for the correct description of in our setup, for the correct description of neutrino masses in our setup, which is a standard model extended by H. And quite importantly, these constraints do not care about the details of how lepton number is broken, because this was parameterized by the matrices X and S introduced beforehand, which have dropped out here. And so these constraints are model independent. Okay, let me now try to explain how we solve these constraints by looking at the quadratic case. Here one obtains two non-trivial complex conditions, or four real ones equivalently, for either neutrino mass ordering. And I explicitly stated these constraints here on the slide. So the right-hand sides of these equations are determined in terms of experimental data. And so what we did is we assigned pseudo-random variates from normal distributions to the parameters occurring in there. And the mean values and standard deviations of these normal distributions we just took from the latest fit results provided by the new fit collaboration in 2020. So that's how we varied the right-hand side. And on the left-hand side, one has 6 parameters, 3 coupling magnitudes and 3 phases. And we only had to vary 2 of them because the rest is actually fixed by the constraint. In the linear case, this in principle works the same way, but here one just obtains one very lengthy complex expression, as can be seen on this slide, which is less instructive to look at. But one sees that here the constraint also depends on the individual neutrino masses M1, M2, and M3, as well as on the totally unconstrained Majorana phases, eta1 and eta2. Okay, let me now get back to an aspect of phenomenology and talk about the decays of a charged lepton into a lighter charged lepton into neutrinos. So in order to describe these constraints, what one can do is formally define different versions of the Fermi constant, depending on the flavor channel which is involved. And since each of these Fermi constants consists of 2 couplings, the ratios of 2 Fermi constants simplify further and involve just the ratio of 2 of these effective leptonic gauge couplings. So this is an equivalent means of describing charged lepton decays. And in the standard model, they are, of course, all equal to 1 because of this feature of lepton flavor universality. But current global fits indicate that there actually is a deviation from lepton flavor universality up to 2 sigma. So here you can see the best fit values, including the 2 sigma regions associated to each of these universality ratios. And now H is a good candidate for explaining these deviations from universality because it contributes to these decays of charged leptons at tree level. And in this fairly recent publication by Krivellin and collaborators, the ranges of 2 of these couplings here, coupling magnitudes divided by the mass of the singly charged scalar singlet, which are preferred by the data at 1 sigma, were determined. So this would cover then the apparent new physics effect in the universality ratios G mu over GE and G tau over GE. And along the way, one would also explain the so-called Cabibbo angle anomaly, which refers to discrepancies in the results of determining the US element of the CKM matrix. So there are direct ways to infer this parameter via looking at, say, decays of tau leptons or of kaons, but there are also indirect ways via nuclear beta decays, because nuclear beta decays determine the UD element of the CKM matrix, and then via the fact that in the standard model, the CKM matrix is unitary, one can infer the US element. The fact that this indirect determination is sensitive to contributions to the Fermi constant explains why if we take H to contribute to the channel mu to E, we would alleviate the tension between the direct result and the indirect result for the US element of the CKM matrix, and thereby at least alleviate the Cabibbo angle anomaly. So now we were interested in how far the explanation of these combined flavor anomalies is compatible with the requirement of H also explaining neutrino masses. Okay, so on this slide, we chose to show only the ratios of the coupling magnitudes for the results of solving the neutrino mass constraints, because the absolute values of these couplings are not directly determined by the constraint. And one can see that apparently a quite non-trivial shaping of the parameter space available for the couplings is obtained that way. In particular, large hierarchies among the coupling magnitudes are disfavored. So let me try to explain the colors which occur here. The small brown area in parameter space indicates where one can find viable solutions to the constraint in the quadratic case, which apparently is a very predictive scenario, which is why the parameters which control this constraint are quite precisely determined by now. And if then one moves on to the linear case, represented by the blue and black sample points, a lot of viable parameter space opens up. So the linear case is depicted by the blue and black sample points here, which distinguish if the universality ratio G tau over GE is explained at 2 sigma only at 3 sigma. But apart from that, there's no further direct physical relevance to this distinction. So we see that this scenario is apparently less predictive, but we find that here it is indeed possible to simultaneously explain neutrino masses and these anomalies related to the apparent violation of lepton flavor universality that I have mentioned beforehand. And the associated parameter space is indicated by the red sample points. So one further assumption had to be made here, namely that that we take the singly charged scale singlet to be the sole driver of explaining these anomalies. While of course there can be further exotic particles around which are potentially involved in the generation of neutrino masses, but we assume that they contribute to an explanation of these anomalies only to a negligible amount. In this still fairly general scenario, we found that this combined explanation of neutrino masses and these anomalies at 1 sigma is possible only in the linear case, but not in the quadratic case, because the brown region is well separated from the red sample points for either neutrino mass ordering. Okay, let me just leave you with a conclusion slide, which states the takeaway message again, which is that we managed to derive constraints for the couplings of the singly charged scalar singlet in terms of neutrino data in a model-independent way. And I also listed a few well-known models of radiated neutrino mass generation here, to which our classification in terms of the structure of the neutrino mass matrix and the derived constraints can actually be applied in full generality, including their variants. Okay, thank you very much for listening to my talk. Are there questions or comments?
Thank you very much. We have some time to take some questions. If you have a question, please unmute yourself and ask. I have a question about the mass scale of this singly charged scalar. So what's the typical mass you want to have?
So the mass is not directly determined by the constraint of explaining neutrino masses. So we just had to assume something, and therefore we just made use of limits which were derived in the literature. And according to these like collider studies that were used for that, the singly charged scalar singlet has to be at least at a scale of say 300 GeV or so. But of course, it can be arbitrarily heavy. So we, for our scans, we covered the whole range of, say, I think 350 GeV up to 100 TeV.
100 TeV.
Yeah, of course,
Okay.
like the larger the mass gets, the less interesting is the induced
Yeah, that's
phenomenology
right.
at low energies. But yeah.
Okay. Okay. Is there any other questions? I don't see any. So let's move on. So let's thank our speaker. Thank you.
Thank you very much.
Our next speaker is Adil. Adil, are you ready?
Yes, can you hear me?
Yes. Could you
Okay.
share your screen?
Yeah,
Okay.
yeah, sure. Let me first share the screen. Share the screen. Okay, so can you see my screen?
Yes.
Okay, thanks a lot for accepting my request to give a talk in this conference. Today I'm going to talk about minimal leptophilic dark matter and the phenomenology of these models in colliders. So this work is based on in a collaboration with Salah Nasri and Ashik Swallah. So it's already been published. Okay, first, let me just talk like a little bit more general about the problems of dark matter. We know actually that there are some problems that actually we believe from gravitational evidence that dark matter should exist with some 80% of the matter budget in the universe. But I mean, despite all this effort that we have deployed, we didn't see any signal, neither in the direct detection, indirect detection, or collider experiments. And basically, this means that we have somehow to change the strategy to go from like freeze out based mechanism, like with weakly interacting massive particles, to more exotic light object or something like this. The thing about dark matter is that the most severe constraints is coming from direct detection, basically, for this mass range as it's shown in this figure. And this means that basically we are going very close to the neutrino floor. This implies that for most of the simple dark matter models, there is a strong correlation between direct detection searches and collider searches, meaning for a given theoretical framework, there is always like this strong correlations, in a sense that if your model give a very like high rate for dark matter direct detection, it should also give a high rate for collider driven cross sections. This will imply very strong bounds and most likely exclude the most simple or minimal models, for example, the singlet model. And so in order to solve this, basically people try to extend the model in a sense that the absence of a signal at the direct detection experiments can be accommodated by the inclusion of some new particles that will ensure some cancellations in the cross sections, and therefore we can still survive these constraints, but at the price, of course, of losing the minimal and the predictive power of the model. On the other hand, if, for example, we use and assume that it's model independent, there is a model independence like constraints on the cross-section, annihilation cross-section from in the absence of signal in indirect detection searches, which means that most of the S-wave annihilation, most of the models that lead to S-wave annihilation channels are already excluded if we, of course, assume 100% of the relic abundance. So there is an alternative solution, which basically we can consider or reconsider the Majorana singlet fermions as dark matter candidates. So this has some very interesting implications. First, the elastic cross section is one loop induced. So basically, it's suppressed even for dark matter couplings of order 1. It's very hard to produce for many models, of course, at hadron colliders. Maybe that's explained why it's not observed so far. An annihilation cross-section is occurs through P wave amplitudes. So it means that already something. So on the other hand, if the dark matter is leptophilic, if it interact only with leptons, then we can use lepton collider as a discovery machines. A last point about this Majorana fermions is that, of course, we can accommodate them in the so-called neutrino mass models, like, for example, the one-loop scotogenic model, three loops or whatever. All of them, they contain at least one singlet Majorana fermion, and they contain more. We want to build kind of a model. Of course, I think it has already been suggested some time ago, which should be based on some like of the pillars of like model within. That, of course, it should be minimal and predictive, of course, which is correlated to each other. Then, of course, should be based on some symmetry. And of course, we can easily embed the model in a grand unified theory. So the simpler the model, the higher the chance we can embed it into grand unified theory. And we already carrying some such a study about like some class of minimal or model of dark matter. So the model is very simple, basically. So we only add two singlets. So basically one is the right-handed singlet Majorana fermion. So it plays the role of dark matter candidate. And we have a charged scalar, which in some papers, it's called like a scalar lepton, because we can always assign a lepton number to the scalar. Those are singlet under the gauge group, basically. And they are odd under a new Z2 symmetry, which ensure the stability of dark matter. So the Lagrangian is very similar to Slepton's Lagrangian, with the exception that here, of course, I have only one state that couples to all the generation leptons, while in leptons, of course, you have for each generation one lepton that couples to them. And of course, because the scalar singlet is electrically charged, so it should couple to the Z and the gamma, and this play a very good role for the production of these particles as hadron colliders. Okay, after electronic symmetry breakers, actually we have like 7 parameters. So one of them is not very important for phenomenology, which is lambda 2. It's affect actually the model indirectly through theoretical constraints, but it doesn't have some important role in collider, for example, or flavor processes. There are 3 couplings for Yukawa, YE, Y mu, Y tau, but actually we can redefine them because it's very hard to constrain one of them at once, but we only constrain a combination, either a product of the couplings of a combination. So basically we define some Yn, which is just the square root of the quadratic sum of the 3 couplings. And we impose a number of constraints on the model parameter space, and we split them into like theoretical and experimental constraints. So the theoretical constraints are similar to the inner Higgs doublet model, or only we have to set the lambda for lambda 5 to 0, and the others can be, all the constraints can be deduced from the inner Higgs doublet model. And here is a summary of the theoretical constraints. I project them as a function of lambda 3 and the charge of the Higgs mass for lambda 2 equal to 2. And as you can see, the white shaded area is the survived parameter regions. And basically, if I want to be in the safe region, I have to choose lambda 3 as order 1 or so, because if I choose a higher value for lambda 3, there is a strong correlation with lambda 2, in a sense that if I increase lambda 2, there is a high risk for this value to be excluded. Of course, there is some region where the Higgs to gamma doesn't constrain the model, but actually because there is a strong cancellations between the contribution of the charged Higgs and the contribution of the W. There is charged lepton flavor violating decays. Of course, the interaction that I have shown, I mean, the main interaction of the model actually violates generation lepton number by 1 unit. And basically it's lead to lepton flavor violating decays at the one loop order. So we can use this make and bar constraints on pressure ratio of L to L prime plus gamma. But the problem is that this doesn't constrain the individual couplings, but the products of the couplings. And therefore we are forced to choose scenarios. And so if we choose YE of order one much larger than Y tau, much larger than Y mu, we can have some like setup that is interesting for E plus E minus colliders. We can do the opposite, of course. We can choose Y mu of order one, and the orders are very small, so that we can be used for mu one colliders. Or we can use all of them to be small, and that can be only do like give some long-lived signatures or displaced vertices at hadron colliders. So we choose the first scenario. For Higgs invisible decay, it's not a problem because only the higher projections constrain the coupling very, very highly. But I mean, for the present limits from LHC, we can still have some window for large Yn. At the Large Hadron Collider, because the interaction looks like this lepton Lagrangian, we can produce charged Higgs pair in pairs, similar to lepton pair production. And of course, we did a reinterpretation of this lepton surge and put some constraints on the parameter space of the model. Of course, here we have a scenario where the decays into electrons is dominating, and therefore we got even weaker limits than the lepton bounds. For dark matter relic abundance, basically we have two regimes. We can have annihilations, which is dominated by annihilation into charged leptons. And we can have, of course, co-annihilations if the mass splitting between the charged scalar and the dark matter is very small. And here kind of a benchmark plots for the relic abundance for different couplings. And basically, as you can see, there is a drop due to the activation of co-annihilation for small mass splitting. And in order to be in line with the relic abundance measurements, you have to have kind of either a large coupling or not very large mass splitting between the charged singlets and the Majorana dark matter. There is actually, what we found actually interesting in this model is that there is a strong anti-correlation between the spin-independent cross-section and the relic density, because the model is simple. So the larger is the relic density, the smaller is the spin-independence cross-section, and vice versa. And for regions where we have large spin-independent cross-sections, we have to rescale by the ratio of the relic abundance in our model with respect to the measured Planck, the Planck measurements. And actually these regions that satisfy at least like 50% of the, like, if we assume that this dark matter constitutes like at least 50% of the dark matter in the universe, it satisfies all the constraints and it can be tested in future colliders, as I am going to show. So now how to test at the International Linear Collider? The easiest way is to produce dark matter pairs in association with something. So we have gamma Z or Higgs, but we choose Higgs because Higgs is somehow more interesting. It has dependence on two parameters, lambda 3 and YE. Of course, beside the masses. For the mono gamma and mono Z, they depend only on the coupling to the first generation leptons. Of course, we can do loop effect. And the interesting thing about this is that, for example, we have like three contributions. We have triangles in the final states, triangles in the initial states, which look similar to the inert Higgs doublet model processes. But we have also a new contribution, which is the box diagrams. And the interesting thing about this box diagrams is that it gives you an idea about what is the particle running in the loop. So if I can measure this process with high precision, including the differential distributions, I can find if there is a particle with a mass something like, say, 200, 300, I can see like some kind of bump in the differential distributions. And maybe we can use this process to like define new dedicated search strategies which are orthogonal to the suggested one, for example, the recoil mass techniques. The other process is charged Higgs pair production. So opposite sign charged Higgs pair production has been studied in different models, and I don't expect there will be a very big difference with our model, but same sign charged Higgs pair production is very interesting. First, because we have mass insertion, because it's a Majorana particle. And second, if you decay this charged Higgs to different leptons, you will have different combination of the Yukawa. So there is here a complementary proof of charged lepton flavor violation at higher energies. And the third thing is that because this violate generational lepton number, the corresponding background are very small. So here we did the kind of, I'm summarizing here the collider searches. So for the same sign charged Higgs pair production, the background are Z, E minus, E minus, and W minus neutrinos, which has very, very small cross section as compared to the signal. And for the signal, the more I increase the dark matter mass, the higher I got for the cross section. So I simply apply like a very, very straightforward selection that I pick up events with two same sign charged electrons with some cuts. For the mono Higgs process, we did kind of a more dedicated analysis, and we assume the Higgs to decay into BB bar so that we can suppress the background. And then we define the signal regions that depend on the mass invariance mass of the BB bar system and the invisible system. And here, like a summary plot, here I'm showing the exclusion bounds. So the violet is from presence bound from the LHC. The green is the extrapolation to high luminosity from the LHC. The navy blue is from mono Higgs process at 500 GeV. The red is from mono Higgs at 1000 GeV, and the gray is from same sign charged Higgs pair production. You can see that the model can be tested in the near, after the at the IRC, of course. Here I'm giving my conclusion. So this is kind of a minimal model, which is, we need to do more studies about this and also with other phenomenologies, because as there are also some analysis for like gravitational waves, etc. The International Linear Collider plays a very unique role to prove and test the model. And the good thing about the model is that it can be easily embedded into grand unified theory. For example, can use SU5 with fermions in the 5 in the Tzen representation, and charges singlet belongs to the Tzen representation, add only one extra singlet fermion, and we can get this Lagrangian. And this is, we are working on this. And thank you for your attention.
Thank you very much. Now it's time for discussion. Do you have any questions? Jonghyun, can you unmute and ask a question?
Hi, Adair.
Hi.
Yeah. I'm just wondering, is there any guiding principle to tell the magnitude of your YE or Y mu? They are all just absolutely free parameter?
Yeah, they are absolutely free parameters. Only the experiments can tell what are the values of these couplings. And so basically, unfortunately for charged lepton flavor violation, it doesn't constrain the individual coupling, but only the product of them. So you have to choose scenarios. But there is no theoretical principle to choose like whatever, 4 or 5 or whatever. Only the limits, the bounds from the experiments.
Okay, thank you.
Any other questions? I have a question. Can you comment on the anomalous magnetic moment of mu1 from the model?
Yeah, well, at the one loop order, it gives a negative contribution, so it cannot explain. Maybe at the two loop order, if for very specific large couplings, we can maybe explain, but the problem is that we need small masses actually to explain the anomalous magnetic moments, which is not what we propose in this scenario. And even dark matter relic abundance cannot explain in the framework of the phase-out mechanism, but maybe you need like conversion driven freeze out or maybe a freeze in mechanism to explain the relic abundance, because the cross section is very small for that.
Okay, thank you very much. Because of time, let's move to the next speaker. Thank you.
Thank you.
So our next speaker is Joy Kanguli.
Yeah, I am here.
Can you share your screen?
Yeah. Can you see my
Yes.
slide, right?
Yes, please start.
Okay, so thank you for giving me opportunity to present my work here. So my work is this neutron mixing by modifying the Yukawa coupling structure of constant sequential dominance. So here's the plan of my talk. I start with the introduction to the sequential dominance mechanism, and then I will discuss about this constant sequential dominance, and then I'll discuss my model, which gives deviation from the CST model, and then the analysis and the model. So starting with the sequential dominance, what is the sequential dominance? That we add 3 right-handed neutrinos to the standard model and write the the Marano, I'd add 3 right-handed neutrinos to the Lagrangian and to standard model and write the Euclid Lagrangian, which is given here. And we're working in a basis where this charge electron mass matrix is diagonal. So here, this we know this LE, LMO, L tau are doublets, and these 3 right-handed neutrinos, this new solar and new deck. So from in these cases, this DEF, ABC, and this A prime, B prime, C prime, all are the couplings. So here to Euclid Lagrangian, the MD can be written in simple form, which is this 3x3 matrix. Similarly, the Marano Lagrangian will be the simplified, which is diagonal, so written here. So as we are getting this MD and MR now with the light neutrino mass matrix form is given by this MD, MR inverse, and MD transpose. So putting all these things in this formula, we can get the light neutrino mass matrix. So before writing this mass matrix, I will discuss the sequential dominance mechanism, which is given by these conditions, which is the hierarchy between this right-handed neutrino masses, like this hierarchy, and the hierarchy between these Yukawa couplings. So these two conditions, when we apply in this mass matrix M nu, and M nu will see that this MD, this is as they are very small, and this will be also decoupled from this model actually. So this will in general will modify to this one. This MD will be 3x2 and MR will be 2x2 because this from this hierarchy we will neglect the third one. So that is the motivation of the sequential dominance, that will start with the 3 right-handed neutrino and it will generally easily go to 2 right-handed neutrino model. So that is the motivation. So now to get more predictivity about this mechanism, we'll constrain this MD more. Like we'll put one coupling to 0 D and one is equal to F and another equal to A equal to B equal to minus C. So putting all these things, we'll get the a simplified form of this MD, which is like this, and MR, which is same as before. So with this MD and MR, if we put this MD and MR in the CISO formula that we know, as I told, so with this get some mass matrix, and we will easily see that this MU can be diagonalized by this TBM, which is this tri by Maxwell mixing easily diagonalized by this TBM matrix. So this is the diagonalized mass. So one is 0 as we are using 2 right-handed neutrino, and another will be given by these two. And we know that TBM, that is tie by Maxwell mixing pattern, which prediction is this. We know the theta 2 3 angle is maximal, and the sine theta 1 2 angle is given by 1 by root 3 and 0 theta 1 3. So that's as it is giving 0 theta 1 3. So that's why we need to modify this CST case, and that's why we have done that. We have modified this MD. That MD was given previously this form. So we have modified to some taking some complex perturbations like that. So then the modified form of this MD now modified to MD prime, which is given this plus delta MD. So with these things, we'll calculate all those mixing and mass parameters that we can see we are getting deviation or not, or all these epsilons we've introduced is I've introduced here all the complex parameters. So the CISO formula we know this modified to MD prime now, so same as the before. So, and then we'll try to diagonalize this m nu s. So to diagonalize this, we'll use this the UPMN as the PDG form of UPMNs that we know like this, which is expressed in terms of three mixing angles, theta 1 to theta 1 3 and theta 2 3, and Dirac CP validating phase, which is defined as delta CP. But but we'll simplify this UPMNs to diagonalize the previous mass matrix. So in simplify, what we'll do, we'll write the sine theta 1 2 and sine theta 1 2 in terms of deviation from the TBM value. The TBM value, we know this 1 by root 3 and this 1 by root 2. So we'll write the deviation as R and S in terms of R and S, so which are very small. Now we also know the experimental ranges of this theta 1 2 and this theta 2 3. So from the experimental ranges, we can easily find the range for R and S, which is given here. This minus 8.82 to 2.52, and this one is for S. And also we know the sine theta 1 range from the experimental value, that is around 0.15. So what we can see here, this if we allow this in this case, they allow non-zero epsilon in our model, we'll get non-zero R, S, and S1. So this is the motivation. So now this is the diagonalization formula that I have told. There is m nu d, which is given by try to diagonalize this m nu s by UPMNs, and this which in general should give the three diagonal mass, neutral masses. So we expand this m nu s and UPMNs up to first order. As we are taking small parameters, so we'll do all first order calculations like epsilon I, R, S, and S13. So all are first order calculations. So we can see that after putting all these things, this may not be in diagonal form, but this will be diagonal. So we'll put off diagonal terms to be 0, which give constants of epsilon in terms of this R, S, and S13, the values of experimental parameters, and the diagonal terms will give the masses. Okay. So before we'll do this, but before doing this, one order of approximation we need here. That is like the masses in the experimental values. So in the beginning we have seen that the masses, the leading order values of the neutrino masses, we are getting this one. One is 0, another one is 3 square by m, and 2 square by m a. So here the sequential dominant conditions demands that e square is greater than a square, like this term should be greater than this square, and this is 0. So we can see that this, we are easily getting the normal ordering of neutrino masses here, as one is always 0, so other one is this, as m3 greater than m2, we are getting normal ordering. So with this thing, we can easily fit this m2 and m3 to our experimental solar and atmospheric values of masses. So that is the order of approximation we are applying here, that a square by m solar should be the solar mass square root of the solar mass square difference square, and a square by atmospheric should be square root of atmospheric mass difference square. And one thing you can also notice in the experimental range, if we put the experimental ranges, you can see that this around S13 range. So this order of approximation should be applied in the diagonalization procedure. So to apply this one, we'll divide the full diagonalization formula by the square root of delta m atmospheric square. So we divide this because we need the order of approximation in this calculation. So now, as I told before, that this UPMNs and mu will expand in terms of cos series of all the small parameters like epsilon I, R, is S13, and this one is added up here. So that is our next, that we will do expansion. So now at the beginning we'll expand the mass matrix up to first order. So this is the 0th order that we already know, that this will give the 0th order, and first order comes because of this delta MD that we have added. These two terms will contribute to the first order. So similarly for the UPMNs case, this will be again two terms. The first order 0th order term will be TBM, that we know, and second first order is in terms of RS and S13 is this delta U is given here. So with these things we'll put in the diagonalization formula, and then we'll try to see what we are getting after diagonalization. So after diagonalization we are getting these two terms. 0th order term that we have seen, this is already diagonalized, and the first order that we need to be should be diagonalized. So from here, these are the extra terms we are getting up to first order. So you can see here that in the first order case, 1 1 2 2 and 2 t is already 0, 1 1 1 2 and 2 t is already 0. So we are getting two non-diagonal off diagonal terms, to which we have should have to put to 0, and this T3 will contribute to the masses of this M3. So here this masses we are getting after the first order calculations, that one is 0 as before, M2 is also the same as the first leading order calculations, but M3 is get modified because of this extra term. Similarly you can see that the off diagonal terms, when you put to them to 0, we'll get two equations. One is epsilon in terms of S13, and another is epsilon 2 minus epsilon 3 equal to twice S. So here you can see that what we were motivated before, that we need S13 non-zero. So then we get epsilon1 to be not equal to 0. So this is the motivation that if we take epsilon to be non-zero, we'll get S13 to be 0, and epsilon1 as we have taken small, and we will show the numerical values of all the epsilons what we'll get. So but in these cases, first order calculations, we are not getting the other epsilons. So that's why we need to go to the second order calculation. The calculations procedure is same, but we'll have to calculate all the epsilons and all the small parameters up to second order. So that is what we have done. Briefly, I wrote that MUS will be second order, will give 3 terms. The 0th and first order is already given before, and second order is because of this 2-wise delta MD, this is second order. And similarly, the UPMNS we write up to second order will be like this. So same, we'll write the equations up to second order. So second order contributions in the after diagonalization will give this term. As 0th order and first orders are already diagonalized, the second order contribution will be coming like that. So 1 1 is coming as 0, but 1 2 1 3 and 2 3 will get non-zero. So we'll put them to 0 again, and 2 2 and 3 3 will add up to masses. So here the masses after second order calculations we are getting. M1 is still 0, so this should come as 0 as is coming, and M2 and M3 both are modified in the second order. And the off-diagonal terms, the constant of epsilons, we are getting here these three equations. To epsilon4 and 5 6 is 0, and these two lengthy equations. And if this phi is introduced here, phi is the Myron of H, as M2 M3 should be real. So we get but in general we are getting complex. So this should be we can eliminate this by this Myron of H that can be absorbed the phases here. So from these equations, we can see that all the epsilons cannot be determined. So let's say we are taking epsilon4 to be free. Other ones can be determined in terms of freely. So epsilon4 we have to assume some small. This cannot be find properly. So for these cases, next we will do this numerical analysis, numerical ranges, and find out all these epsilons at what we are getting, what we have assumed, and what we are getting. So to do this numerical analysis, we have taken the solar atmospheric masses to be their best fit values, like this one we know from the neutron oscillation data, and mixing angles and the CP violation phase to their 3 sigma ranges, which are given here. So now, as we were told in the beginning, the epsilon are complex. So we have resolved into two parts, that is real and imaginary part. So as I discussed, there are many equations, 3 and in the first order 2, 5 equations are there. So we can get all the epsilons and the numerical values of the epsilons like that. The real epsilon, imaginary epsilon, and real and imaginary parts of 2 and 3. So this we can see that these are small, at what we assumed around 0.2. So there is no problem with that. But as I told, the epsilon is a free parameter. So epsilon we have taken to be 0.1, and phi have taken for simplicity take 0. So with this 4, we have varied the epsilon 4 to be 4 values and found the ranges of epsilon 5 and real and imaginary parts of epsilon 5 and epsilon 6. So with these things, we can see that let's say for one value 5 0 and epsilon for 0.1, we can see that mod of real epsilon 5 and mod of real epsilon 6 to be coming as little large, like 0.4. This 0.46 and 0.37. So let's say 0.4. But this should not be that large, it around 0.22 or 0.23. So that's what we have done. We have restricting this mod of real epsilon 5 and mod of real epsilon 6 around 0.23 and 0.23 to then I found what are the ranges about mixing angles and delta CP. Delta C for one cases we have done that phi equal to 0 and epsilon 4 equal to 0.1. So this is the thing that mixing angle versus delta CP. The region allowed is given by this one, and the exclusion, which the region excluded for this mixing angle, is this one. And for this sin square theta 2 3 and delta CP is this one. This region is excluded for this real epsilon 5 and real epsilon 6 to be around 0.23. And you can see also the sin square theta 1 3, all the experimental ranges are allowed. So there is no problem with this. So these two things, some regions are disallowed. So next, the numerical analysis is done. Now next, as we have proposed some MD like modified to CSD by taking some small epsilon parameters, but in general that should be proposed, but that should be justified from some flavor model. So this is the flavor model which justifies the Dirac mass matrix structure. So the model is comprised of this SU3 and 2 Z3 symmetries, which composed of 4 triplet fields and 3 singlets and 2 right-handed neutrinos. So the Euclid Lagrangian can be written as this one. So first two terms, that phi n, phi s, and this MP is the cutoff scale, which is the Planck scale we have taken. So as phi n, phi s, when you give wave to phi n, phi s, this will give the leading structure that already in the CST structure, that is, there's no epsilon there. And then these two terms, the zeta and phi n, phi s prime, when you give wave to these two, this will give the modified modified Dirac mass matrix, that is delta MD. And when you give this chi n, chi s to wave, this will give the wave Majorana mass matrix structure. So let's discuss this one. Let's say we'll give this wave of phi n, phi s to be this form. That is ya and ys of order 1, and this I taken 0, 1, 1 and 1, 1 minus 1 to get the form. And this we don't need to prove this, because this is already in the literature that we can get this kind of wave structure of these two fields. And then for our case, that how we get the small epsilon, how do we explain the small epsilon in our model? So we'll give this phi n, phi s to be simple, like order 1 parameters, that is simple y1, y2, y3, simple. Similarly, y1 prime, y2 prime, and y3 prime. There is no problem. And we can take this order 1. All are non-equal, not equal. And but this zeta wave we have chosen such a way that this should give the small epsilon. Like we have chosen zeta by MP, like in this parameter Lagrangian, we can see that zeta by MP is there. So this zeta by MP have chosen to be small epsilon. So that's why multiplied by small epsilon will give our structure. Similarly for epsilon 1, 2, 3, and similar for the other case 4, 5, 6, 2 column. So, and also we are getting what we have started with, that we can prove this mass matrix, Dirac mass matrix, by giving this scalar fields to the appropriate wave. So let's discuss about the wave, the range of the wave, that in which order they are all the fields are getting wave. As in our model, there are many scalars. So you can see that these two, as I've told, this chi and chi s generate the Majorana mass matrix, right-handed Majorana mass matrix. So this should be in the range of 1 TeV. Now the zeta is giving the explanation for the smallness of these epsilon parameters. So this in general should zeta by MP should be 0.1 and 0.1. So MP is the Planck scale, so we can get zeta about 10 to the 17 GeV. So now again similarly, that the neutrinos, we know the mass range should be order of 0.1 eV. So then we also get this 4-triplet scalar to be order of 10 to the 12 GeV. So from these 3 points, we can see that the ranges of the wave are very different. There is a large hierarchy among these wave. But if we write the scalar potential of the full model, and if we fix the parameters in the model, we can easily get the structure. So this is not discussed here, but this is discussed in the article. This is explained, that writing the scalar potential and the order of parameters we are getting for this, demanding these to be the waves. So this is the also in the conclusion. At the end, we can say that what we have done. So in this work, what we have attempted to explain the neutrino mixing in order to explain the neutrino oscillation data. In here we have considered a model where we modified the Yukawa coupling of this CSD model, described CSD model, by introducing some small epsilon parameters. Then we followed an approximation procedure order to this diagonalize the mass matrix of the CSO formula, and then we computed expressions of the second order level to neutrino masses and mixing in terms of this epsilon. And then using the expression, we have demonstrated that neutrino mixing can deviate from the TBM pattern by choosing appropriate epsilon I. And then finally, we have constructed a model in order to justify the neutrino Yukawa couplings of our model. So these are references. Thank you.
Thank you very much. Now it's time for discussion. Do you have any questions? Or comments? Okay, I have a question. So before introducing epsilon parameters, your theory produces try by maximum mixings, right?
Yeah. Because
and
this
you deform it.
Yeah, this is already produced, and this is all in the literature. So we have modified the structure.
Right,
actually.
and you deform the model by introducing small parameters.
Yeah.
So you, as far as I see, you introduce 6 complex parameters, right?
Yes, right.
Okay. So having that, having 6 complex parameters, you actually have 12 parameters.
Yes, right.
But so how many parameters you want to fit using your 12 new parameters?
Means, can you repeat once because I have some problem? Yeah. How do I fit?
I mean, we have a finite number of observables.
Yeah.
And by introducing new parameters, we can always try to fit the data.
Yes.
So my question is, how many actual physical observables you want to fit using your 12 real parameters or 6 complex parameters? That's the question.
As I told that one of them I have taken as free because all of them we cannot fit. Otherwise, means in terms of the epsilon 4, like you can see that the ranges, masses, and the mixing is in terms of some combinations of the epsilons. So that is the main requirement here. The combination of epsilon, not all the epsilon separately. That is one thing.
Okay, thank you. Do you have any other questions? Okay, thank you. So let's move on to our final speaker of this session.
Okay.
Thank you very much, Joy.
Thank you.
So now is Sati Brata's turn. So can you unshare your screen, Joy? Joy, could you stop sharing your screen?
I have some problem. 1 minute.
Oh, is it right?
Not get. Okay. Thank you. Yeah.
Oh, thank you.
Oh, okay. Can you hear me?
Yes, I can hear you. Please share your screen.
Yeah.
Okay,
Can
I
you
can
see
see
my
your
screen?
screen. Good.
Okay.
So now please start.
Yeah. Okay. At first, I would like to thank the organizers for giving me this chance to present this work at PASCOS 2021. I'll talk about mu1G-2 and Zenon-110 excess with dark matter in L mu minus L tau model. So this is a work which is based on these two. This talk will be based on these two works, which are done in collaboration with Devasis Bora, Dibyendu Nandan, Narendra Sahu, and Manoranjan Datta. So the motivation for this two work is to address the recently, two anomalies which were recently in news. One is the lepton flavor universality violation by the observation of mu1G-2 at the Fermilab's mu1G-2 experiment, and the other one is the observation of electronic recoil excess events at Zenon-110, which was reported in June last year. So in this context, we revisited one of the most well-motivated extension of the standard model, which is L mu minus L tau model. And this is well-motivated because this L mu minus L tau is naturally anomaly-free, and it gives a natural explanation to mu1G-2, as well as it can have very interesting phenomenology to neutrino mass and dark matter. And when I say interesting dark matter phenomenology, what I mean is that in such models, both DM and SM can have can be charged under the new gauge extension, so that the DM-SM interaction doesn't always have to happen through the kinetic mixing. So, and it also has better perspectives of detection in context of the various muonic probes that I will discuss. So the symmetry of the model always allows for a kinetic mixing term, which is given by this epsilon by 2b alpha beta y alpha beta. And even if you neglect this term at the tree level Lagrangian, it will always show up at the loop level because of the particles that are charged under both the gauge groups. So those particles will run in the loop, and you can always have a mixing between the two gauge bosons. So coming to the anomalous muon magnetic moment, we know that magnetic moment of muon is given by this, where G mu is the gyromagnetic ratio, and for any structureless spin half particle, this is equals to 2. And if any radiative correction couples to the muon spin, then it contributes to its magnetic moment, which is given by this equation 2. And in our model, basically in LMU minus L tau model, the loop diagram, which is mediated by Z prime boson, this additional contribution to the mu is given by this equation 3, and it depends upon the gauge coupling G prime or Gx and the gauge boson mass mz prime. So always in any LMU minus L tau model that you consider, this is one constant that will always be there on your parameter space. I mean, this will put constraints on the gauge coupling and the gauge boson mass. So the recent status of this muon anomalous, as I said, this mu is the quantity that we measure. So this has been predicted in standard model to a very great accuracy, and it has been measured through various experiments to at very good precision. And after the observation of this muon G minus, after the measurement at Formulab's E989 experiment. So now the status of delta mu is at 4.2 sigma deviation from the standard model. So coming to the second anomaly that I was talking about, that is the result which was reported by Jen and Munton collaboration on observation of excess of electronic recoil events. And there were many possible interpretations. 3 of them were proposed in the Jen and Munton paper itself. One is the solar action interpretation, neutrino magnetic moment, and beta decay from tritium. Though solar action and neutrino magnetic moment can address this result at 3.2 and 3.5 sigma significance, but they are in strong tension with stellar cooling constants. So particle physics community focused on many alternative interpretations like dark matter and cell non-standard interactions of neutrinos. So I will focus on the dark matter interpretation of this Zenon-Munton electronic excess result. So there can be 2 possible scenarios that I will discuss. One is the inelastic dark matter scenario, and another one is the boosted dark matter scenario. So in the inelastic dark matter scenario, we basically have 2 component dark matters. The heavier dark matter will downscatter to the lighter dark matter, and thereby imparting some recoil energy to the electron that is observed at the Zenon-Munton. And in the boosted dark matter scenario, a boosted particle, I mean, not the standard cold dark matter velocity that is 0.001, but dark matter with a higher velocity can elastically scatter up the electron at the Zenon-Munton and can give rise to the Zenon-Munton electron recoils that we have observed. So in this context, I will, as I said, I will discuss 2 scenarios. One is the inelastic dark matter, and another one is the boosted dark matter. So let us first discuss about the inelastic dark matter scenario. So here we have the dark matter field is denoted by this Dirac fermion chi, which has a LMU minus L tau charge half, and it is naturally stabilized because of this LMU minus L tau gauge charge selection. So we do not need any additional symmetry to stabilize this dark fermion. And we have a scalar phi1, the wave of which breaks the LMU minus L tau gauge symmetry, thereby giving mass to the corresponding gauge boson. And since this chi is a Dirac fermion, so it has a bare Dirac mass. And because of its coupling with this scalar phi, it can have a small Majorana mass. So after the LMU minus L tau symmetry breaking, it can split up into 2 pseudo-Dirac mass states or 2 Majorana states. And in the physical basis, the Lagrangian can be written like this, equation 8. And here you can see that in such a scenario, in this pseudo-Dirac scenario, the vector interaction is always off diagonal, and the diagonal interactions are always of axial vector kind. And if you calculate the mass splitting between the 2 states, then it is given by this 2m plus, where m plus is nothing but ml plus mr by 2. And for our consideration, we have fixed this mass splitting at keV scale, which is relevant for the electron recoil excess events reported at Zenon-Munton, because the electron recoil events, the excess is observed in a range 1 to 7 keV. Now coming to the relic abundance of these dark matter components, so we solve these 2 Boltzmann equations to get the relic abundance. Here you can see that the first term is basically the annihilation term, and the second term is the interconversion term, and the third term is the co-annihilation term. And as I mentioned, that the mass splitting between these 2 components is maintained at a keV range. So because of that tiny mass splitting, the interconversion or the subdominant, the interconversion between the 2 dark matter components, that becomes subdominant. However, the co-annihilation process, they become very efficient. And since these 2 components have identical annihilation channels and their interconversion is almost suppressed, so we get almost identical relic abundance for the 2 dark matter components, and that can be observed at this right panel plot. So here this resonance feature is because of the S-channel mediated diagram, S-channel diagram, which is mediated by the gauge boson. And okay, whatever I said now is fine, but in the left panel figure, we have shown the interaction rate of various relevant processes as compared to the Hubble expansion rate. And this is to show the fact that how L mu minus L tau is L mu minus L tau model is different from any other secluded U1x extensions of the standard model for dark matter phenomenology. Because as we see that even U1x secluded U1x extensions, the dark matter is completely I mean, dark matter interaction with the standard model is always through the kinetic mixing. So DMSM interaction is always epsilon suppressed, and they can decouple from the chemical, they can always decouple from the thermal bath at very early epochs. However, the interconversion between the dark matters, which are purely through the U1x interactions, they can continue till later epochs, thereby thereby changing the relative abundance of the dark matter components. But in L mu minus L tau model, what happens is that this DMSM and DMDM, since both dark matter and standard model particles are charged under the gauge group, they almost decouple at the same epoch. Thereby, the reason of getting two equal relic for both the components is satisfied. Now, another constraint that we need to explain the general quantum is that both the dark matter components should be present in the present epoch of the universe, which implies that the chi2 decay or chi2 lifetime should be greater than the age of the universe. As I said that we have maintained that mass splitting between the two components at 2 keV, so there is always a decay mode, this three-body decay like chi2 going to chi1 and nu r, which is mediated through Z prime. So the lifetime of this chi2 should be greater than the age of the universe, and this always puts a very stringent constant on the parameter space, as I will show in my summary plot. Now coming to the Zenon quantum electron recoil excess. So the excess is explained through the downscattering of the heavier dark matter component. And this is the differential electron scattering cross-section rate, where KERQ is the atomic excitation factor and F of Q is the dark matter form factor, which we have assumed to be 1. And this F of V is the velocity distribution for the dark matter. And in the Earth's rest frame, it is a Maxwellian velocity distribution. And after the angular integration, we get this form in equation 12. And for any inelastic scattering, the limits of this integration Q minus and Q plus are determined by relative values of the electron recoil rate and the mass splitting, which are given by this. And one interesting feature for any inelastic scattering scenario is this peak that we get when we integrate the atomic excitation factor times the momentum, and we do a momentum integration of that quantity. So as you see in the left panel plot, this is the atomic excitation factor as a function of the momentum transferred. But when we integrate it, we see enhancement at ER equals to delta M. So the fact that why this happens is that, as you can see, that Q plus and Q minus involves this quantity ER minus delta. So when ER becomes equal to delta, this Q minus, the lower limit approaches 0, and this quantity essentially gets maximized. So that is the reason we get a peak. So now for the final recoil energy spectrum, this is the differential event rate, where NT is the number of atoms in the Zenon detector, and chi2 is equal to the dark matter number density, and which is equal to the total number density of dark matter at the present universe divided by 2, and this is the differential scattering rate. And to get the final detected recoil energy spectrum, we have to converge this equation 13 with the energy resolution of the detector, which is given by equation 14, where this gamma E is the detector efficiency, and this is given in the Zenon quantum collaboration paper. So we have adapted that, and finally we calculated this detected recoil energy spectrum, and this is the result. So here, as I was saying, that for inelastic case, the velocity is typical CDM velocity, which is 1 into 10 to the minus 3, and the corresponding cross section that we get for the electron scattering is of the order of 10 to the minus 17 GeV minus 2. So this is the final result, where we have put all the constants in the plane of Gx versus Mz prime, and this orange line basically shows the G minus 2 mu1 G minus 2 value at 3 sigma, and this pink line is the line that we get from the Zenon-Munton fitting. So after incorporating all the constraints, we see that only a very tiny triangular region of parameter space is allowed, and you can see that most of the parameter space is ruled out because of this constraint on the lifetime of the heavier dark matter component. So after the publication of the mu1G-2 result by the Fermi lab, we thought of exploring this boosted dark matter scenario, because now we need only a single component dark matter instead of two component dark matters, and this dark matter will essentially annihilate into a boosted light particle. The idea is this, and dark matter will annihilate into a boosted light particle, which will scatter up the electron at the Zenon-Munton detector, and we can get the required excess. So here we have two vector-like fermions psi A and B, and a singlet scalar eta. The LMU minus L tau gauge charge of gauge coupling of these particles are respectively 0, GB, and 0, and this is the relevant Lagrangian. Here GB is the gauge coupling of psi B with the Z prime, which is essentially NB into G mu tau, and since NB is the gauge charge, which is a free parameter, so we keep GB as a free parameter. And we tune the Yukawas of this YA and YB, the Yukawa of psi A and psi B with theta, to get the desired phenomenology. So now coming to the relic of this scenario, so we solve these three Boltzmann equations, where eta is a scalar which is initially in thermal equilibrium with the standard model, then it freezes out and it decays to psi A, and psi A can have conversion process as psi A is annihilating to psi B, so psi A can deplete. Psi A can also annihilate to the scalar J, which is the scalar responsible for the psi A to psi B annihilation, and this eta is producing the psi A number density, and psi B is getting its abundance from psi A annihilation, as well as it is depleting the number density through its annihilation to PP, where PP can be Z prime Z prime, and this J. So this is a very important part, because of this gauge interaction of psi B, which is very dominant, the number density of psi B will always be suppressed. So this is the plot that we have shown for benchmark values. So here this red line and this green line are the equilibrium number density of eta and psi A and psi B. So as you can see, the eta decouples from the equilibrium and it saturates, but in presence of psi A and psi B, okay, if we do not invoke the eta, then psi A essentially freezes out with a number density which is very, very less than the required number density for the observed relic. But when we invoke the eta, decay of eta, which is a non-thermal contribution, so it essentially increases the number density of psi A, and once the psi A number density increases, it again annihilates to psi B, which also increases the psi B annihilation. So the final number density of psi B is a result of its annihilation from psi A, its production from psi A annihilation, and the annihilation of psi B to Z prime Z prime. So this is the psi B abundance, and this is the psi A abundance. So basically psi A is the dark matter, and psi B is a very subdominant component which can be produced in the present universe at dark matter dense regions from psi A annihilation. Coming to Zenon-Munton electron recoil excess, so now we have a elastic scattering of the psi B with electron, but this psi B has a typical velocity which is boosted one, not in the 10⁻³ order, it is in the 10⁻² order, like 0.05 or 0.6, and these things are again same. As I said, psi A is the dominant dark matter component, so it can annihilate in DM dense regions at the present universe. So it can be produced in, the psi B can be produced in galactic centers or sun. And essentially the boost of psi B will be determined by the mass difference between the psi A and psi B. And the flux, if we consider that the source is from galactic center, then the flux is given by this equation 18. So using this flux, we calculated the differential scattering, differential event rate, and the plots are as shown here. So here we have assumed the velocity as 0.05, and you can see that such kind of velocity can be obtained if the delta m is of the, delta m by mb is of the order of 10⁻³. And here the cross section is of the order of 10⁻11 GeV-2. Now coming to the final summary plot. So you can see a very tiny region of parameter space is allowed after incorporating all the relevant constraints, And this interestingly, this parameter space is within the sensitivity of these experiments like NS62 and NS64, so it can easily be probed in the future experiment. Now, once we decide the allowed parameter space in the G mu tau versus MZ prime plane, we can then turn to the dark sector and see for the allowed parameter space in terms of GB and this annihilation cross section of A to B. So as we can see, if we decrease this annihilation cross section, then what happens is that the psi B flux essentially decreases. So in order to explain the general Montan excess, we need a larger GB, which is clear from this right panel plot. So to conclude, I will say that future data from ongoing and near future experiments can probe this entire parameter space of this very minimal and predictive model. Thank you.
Thanks a lot. So now it's time for questions. Do you have any questions? Okay, since you introduced several particles, could you let us know what particle should be the target for the future experiment?
Okay, MZ prime should be the target because the final parameter space that we have shown is in the plane of G mu tau and MZ prime. So we can basically probe that whether we can get a boson, a Gauss boson of this mass and this coupling, because this can essentially explain both mu1 G minus 2 and Zenon Montan simultaneously.
Okay, very good. So any other questions? Okay, if not, let's thank our speaker once again. Thank you.
Thank you so much.
Okay, so this is the end of the session. I think okay, so we have 30 minutes break and we will resume at 3:30. Okay, see you soon. I think you can stay if you like.